Morning.
Good morning.
Morning, Sarah.
Morning. I've got two quick questions. First one, for SAS, I know, for example, in Stata, you've been showing for the regression, you want to test the difference between two means, you can specify mean from category A, group B, minus mean category A, group B. Is there a way to do that in SAS, or do I have to look at difference between all means? For example, contrast and diff means seem to give me everything.
Yeah, so in contrast, the key about the regression approach is that you'd want to look at these contrasts adjusting for their covariance. And you're not going to get that from survey means. So you would be able to use a contrast statement within survey reg to do something like that. Yep.
Okay, and could I specify the individual categories if I in the document?
Yeah, so again, take a look at the syntax on the ASTA website, but you'd specify contrast between individual parameters in that regression model. So you have to list the names of the parameters and what their corresponding coefficients would be.
Okay. Second question, for histogram, if I'm comparing histograms to look at the distribution of the underlying variables.
Yep.
Does it matter if I look at the weighted or not? It's seeing just the observation values shouldn't be fine, right? Because I don't think there's an automatic way to do that.
Yeah, I mean, you could look at a weighted histogram if you want, but again, what we really want to look at is the histogram of the residuals, not the variable itself.
Okay.
So again, I could make up a wildly non-normal histogram for you, and a linear regression approach would still be perfectly fine. Okay. So you really want to look at the conditional residuals based on the fitted model.
Okay, makes sense.
Yep. All right, good morning, everyone. We'll get started in about another minute or so here. So. All right, well, good morning again, everyone. I think we're going to go ahead and get started. So today, the agenda, we're going to be going over lab session number 4. So hopefully everybody has that open here, and our focus is going to be on linear regression. So we'll look at some examples of linear regression analysis using both Stata and R. And then remember that today by 5 p.m. your drafts of your introduction and data methods sections are going to be due. So we'll do our best to take a look at those over the weekend and get back to you early next week with feedback and make sure you're on the right track and everything. That's really the objective here. So looking forward to reading those. I've already received a couple, and we'll look forward to receiving those over the course of the day today. And then next week, actually on Monday, we're going to have a guest lecture by Young Chow. So Young Chow is going to be talking to us about logistic regression. And then Wednesday, we're actually going to have our lab session related to logistic regression because there's no class on Friday due to the July 4th holiday. And then again, we're having a party at our house on July 4th next Thursday, okay, for everybody to join. So everybody's welcome. And Raphael and I are talking about different transportation options. So we'll be in touch about that. Okay. So that's our agenda here moving forward. Before we get into today's lab, are there any general questions about linear regression, conceptual, practical, anything in that regard before we dive into the actual syntax here? Any questions? Yeah. Yep.
With the T table function to create table 1 in the survey design, do you see any problem with that?
What do you mean by 1 by 1?
Binary.
No, yeah, you want to do the actual analysis 1 by 1. I'm not sure what you mean by D table. You want to do the analysis of the individual predictors 1 by 1. So can you clarify what you mean by D table? I'm not sure what you mean.
Do the D table and then do the Y.
As long as, I'm not familiar with it, but as long as that function works with the complex sample feature commands, that's okay. If that function does not accommodate those commands, then it's off the table. Okay, so make sure that if whether it's reading in output from the survey commands or actually accounting for design features themselves, make sure it's actually doing that. Because if that function is just using standard regression procedures or standard bivariate analyses, it's not relevant for what we're talking about. Okay, so if it's some kind of user written function or something like that, just make sure it can accommodate the estimates produced by the survey procedures. If not, then we can't use it. Okay, other general conceptual questions about regression in general or any of the techniques that we've been talking about this week? Does everybody feel pretty much up to speed on those? Questions, comments? Everybody's good? Okay, let's jump in then. So in this 4th lab session, we're going to be using Stata and R for design-based linear regression. And we're also going to consider diagnostics. So especially in R, I want to illustrate the use of functions in the SBY diags package that give you design-adjusted linear regression diagnostics, but we'll still look at basic diagnostics in Stata as well, like we've talked about in the lecture thus far. So we'll use a variety of post-estimation tools after fitting these different models. And we'll also talk about some of the fundamental data management tasks in preparation for fitting these kinds of models. We're also going to illustrate how to test for the importance of weights when fitting regression models. We talked a lot about that on Wednesday and that kind of general debate in the literature. So we'll talk about how to evaluate that more formally as a part of fitting any type of regression model, not just linear regression, but any type of regression model here. Okay? And again, for more details, refer to chapter 7 for additional theoretical background, additional practical examples. Some of the email questions, just remember that there are readings in this class. I know there's a lot going on and it's very busy with the other courses, but a lot of the email questions have just been pointing people to sections of the book. Okay, so don't forget that the book does contain additional details, references, information on top of what we're talking about in lecture. So always refer back to the book for additional details. There's a lot of stuff in there that can help answer, I think, the questions that you might have. So don't forget to refer to the book as you're working through this stuff. Okay, so let's start with Stata. And I have copied the Stata code to a new do file editor within Stata here. So as we've done in prior labs, we're focusing on the NHANES data. I'm going to read in the data, set my working directory, read in the data, start a log, and then set all the variables to lowercase. So same block of commands that we've used previously. I'm just going to go ahead and run all of those commands in one block here, since we're now pretty comfortable with what's going on there. Okay. So I now have the NHANES data. I have everything renamed to lowercase, and I'm ready to go within Stata. All right, I'm going to set my design features using survey set. Again, listing the cluster codes first, the exam weight second after P weight, and then the stratum codes after the strata option. Okay, go back here, make sure that that's all set, no major issues there. All right, again, hopefully everybody's pretty familiar with that approach at this point. And then I'm going to create now a 3-category version of age to use in the example that we're going to be talking about for BMI, where BMI is our dependent variable in this particular model. So again, same stuff we've talked about previously. When you recode in Stata, make sure that you're careful about how missing data are handled. So notice my category 3 of age ensures that I'm not resetting missing values of age to be category 3. Okay, again, hopefully if you're a Stata user, you're familiar with that at this point. So I'm going to run this entire block all in one swoop here. Okay, double check my frequency table for the adult population, and everything looks good. Not seeing any missing data or anything. Remember that it's okay to look at these simple descriptives without any kind of weights on, just to get a sense of the data management steps and make sure everything looks okay before you move forward. Okay. All right, so I have my 3-category age variable. Now we're going to start with a simple linear regression model of the untransformed BMI dependent variable. Okay. Now, one thing to note here is the use of factor coding for all of these different predictors when we're setting up this model. So as predictors of BMI in this case, I'm considering gender, marital status, education, and age category with 3 categories, all right? All of those are categorical. So they're all being listed with IDOT in this particular model. We're also using an unconditional subpopulation analysis. Okay, so again, given that age 18P dummy variable, we're making sure that we're not deleting kids. We're keeping everybody in the data set, and then we're fitting the regression model just to that subpopulation. Okay, so reminder of the regress command, dependent variable listed first. In this case, it's continuous BMI, body mass index, in the NHANES data set, followed by the list of predictors that we want to focus on that we think are theoretically relevant. All right, so I'm going to go ahead and fit this model. And we'll take a look at the output here from fitting that model after the model is estimated. So remember, for your drafts today, introduction, data, and methods, part of that is going to be your statistical analysis plan. So if I was fitting a linear regression model, which is what Stata is doing right now, I'm describing what estimation and variance estimation methods I'm using as a part of that statistical analysis plan. So if I'm writing up this linear regression model for my draft right now, what am I saying is my estimation method for linear regression? What method am I using to estimate these parameters? My parameters. What method am I using to estimate my parameters in this model? Not the variances yet, but the parameters. Weighted least squares. Weighted least squares. So if I'm writing that statistical analysis plan, I'm saying I fit a linear regression model with BMI as a dependent variable. I used weighted least squares for my point estimation of the regression parameters, those finite population parameters. What am I saying is my variance estimation technique, Jupiter? Now I'm saying I'm using linearization for my variance estimation technique, which is the default in survey regress. Okay. Those are the sentences I would write in my statistical analysis plan if this is what I was doing. Right? Very clear? Okay. So in this table of output from running survey regress, let's take a look at what we have. As we would expect in this NHANES data set, 14 strata, 31 ultimate clusters or CQs, if you will. Let's look at the kind of default output here at the upper right. We see the total number of observations in the data set, and then the subpopulation number of observations, 5,230. That's different from 5,864. Okay, why? Why is that sample size different?
Weight.
Say again, Carrie?
Weight.
Not the weights. Weights are available for everybody? Why are we
There's-
losing 600 cases?
There's some missing values someplace in.
Right. Item missing data on the variables going into the model. Remember, this is a multivariable analysis. So Stata is deleting cases with missing data on any of those variables that are being input into this regression model. Okay. And it just so happens that we're losing 600 cases, right? And this gets back to an earlier homework assignment. What if those 600 cases are systematically males? Or they're systematically different in terms of their BMI? Is this introducing bias? Okay. So by default, survey regress is using list-wise deletion. And it's getting rid of cases with item missing data on the predictors of interest. So we have to ask the question, now if we're losing 5 or 10 cases, fine, probably not gonna make a big deal. In this case, we're losing 600. Okay. Are those cases somehow unique? We could do some additional data management, do some exploration to look at the characteristics of the cases that are being dropped. And perhaps some type of imputation approach to deal with the missing data would be beneficial. Okay, we're going to talk about that later on in the class. For now, let's just make the assumption that more or less the 5,230 are a simple random sample, okay, of the actual subpopulation. All right, so design degrees of freedom 17, we see an F statistic. Okay, what null hypothesis is that particular F statistic testing? See an F statistic of 9.67 with a p-value of 0.0008. What is that testing?
That all the, there's no relationship between the dependent variable and any of the independent variables on the models, or that all of the estimated coefficients are 0.
Right, exactly. Thanks, Sarah. So we're testing that all of the coefficients in this particular model are equal to 0, okay? And if we go through and count those coefficients, we have 1, 2, 3, 4, 5, 6, 7, 8. There's your 8 numerator degrees of freedom, okay? For that particular F test. The 10 is a function of the design degrees of freedom and how many parameters that are being estimated here, okay? So based on that test, that overall test for the model, what decision do we make about that null hypothesis that all of those 8 coefficients are equal to 0?
Model overall is significant. Model overall is significant.
Yep, the model overall is significant. Does this tell us which of the coefficients are different from 0? No. This just tells us that at least one is different from 0. It does not tell us that all of them are different from 0. It does not tell us which ones are different from 0. It just rejects that null hypothesis. Okay, at least one of these coefficients is different from 0. All right, that's that design adjusted F tests based on the weighted estimates and the linearized variances and covariances that we were talking about in lecture. So it's nice that Stata gives that to you overall, because if that test is not significant, we're back to the drawing board, right? All the coefficients are 0. Okay, so good news in this case. However, look at the weighted R squared of this model. Okay, these particular predictors that we've selected right now are only explaining about 2.8% of the variance in this dependent variable in the larger population. That's a weighted R squared. All right, so it's a start, but there's probably work to be done in trying to explain more of the variability in this particular physical measurement of BMI. Okay, and we can hypothesize what other predictors we haven't included that might be relevant for this particular outcome. Okay, now we can look at the actual point estimates, the linearized standard errors, and the corresponding tests of significance for the individual parameters. If you look at those individual t-tests, it really doesn't look like a whole lot's going on, okay? We see a significant result for the 4th education category relative to the 1st. So it seems like highest education reduces the mean significantly relative to the lowest possible education. All right. We see a significant result for the second age category relative to the first. So it looks like age category 2 has a significantly higher mean BMI than age category 1. So middle-aged individuals have a higher BMI than individuals in the lowest age range. But there's not much else going on outside of that. Okay. What about MERCAT? Look at marital status. Okay. Neither of the individual parameters is significant, but okay, what are we not testing in this particular output? We're comparing 2 to 1. We're comparing 3 to 1. What are we missing? 2 to 3, right? So it would be naive to look at this output and say, marital status doesn't matter. Okay. What tests do we have to do to formally test whether marital status matters as a predictor? What tests do we have to perform to do that? LINCOM, what was that command that we talked about in lecture that allows us to test multiple parameters? What was that command? Starts with T,
Test.
then E, test, right? After fitting this model, we can say test, and then list the parameters that we wish to test. Okay, again, 0. So if I'm testing whether marital status matters overall, I can say test 2.MERCAT and 3.MERCAT. That's how I refer to those two coefficients that are saved in the output here. Okay, this is testing whether both of those parameters are equal to 0 simultaneously, giving us an overall idea of the importance of marital status in the overall model. Okay, so that very simple command gives me that partial f-test of the importance of multiple parameters at once. So if I go ahead and run this, it looks like even with that additional contrast of 2 versus 3, marital status still doesn't really seem to matter for BMI when I take these other covariates into account. So if I wanted to simplify the model somewhat, I could probably drop marital status. But if I was using a 0.1 level of significance, I have evidence here to retain it. So I have marginal evidence of the importance of marital status. Okay, but that's how we get that overall idea, not by looking at the individual t-tests, but by looking at the overall test of the importance of marital status. Right, so there's my design adjusted f-test for that particular hypothesis. Also looks like it can eliminate gender. Okay, but remember, this is not testing interactions. Right, we're just looking at the main effects, quote unquote, of these predictors. If gender in fact moderates the relationship of some other variable, dropping it would be a mistake at this point, right? Because it may play a very important role in moderating the relationships of other variables. So before I get rid of predictors entirely, I want to make sure that I'm not interested in testing any interactions involving those predictors, because they don't have to be significant here to be important for interactions. It's a very common mistake that data analysts make, and it has nothing to do with survey data. We got to be careful about that. All right. So we see a couple of significant results, but again, looks like there's certainly some work to be done. So after fitting that model, I can look at my residuals and predicted values. So the two subsequent predict statements, the first statement creates a new variable in the data set called E-hat1, okay? That's going to contain my raw residuals based on that, the weighted estimates of the coefficients in that model. So if I run that first predict statement with the resid option in the data set, if I just look at the data set here up top, all the way on the right-hand side, I'm going to see saved residuals for the cases that were actually analyzed in the fitting of that regression model. So I'm going to see 5,230 saved residuals for the cases that didn't have missing data. Okay, and I can go through those raw residuals and take a look at outliers, cases that were very poorly fitted based on the model, look at the distribution of the residuals, et cetera, et cetera. But now I have that variable in my data set and I can do with it what I want. That's the key point. And that comes about by using the resid option. Okay, I can also save the predicted values. So notice that the option for saving the predicted values is XB. Basically, it's an option that says save the values based on the regression function. The predictor is multiplied by the estimated coefficients, and we're saving those values in a new variable called p hat 1. All right, so if I run this line now, and I look at my data again, now I have both the residuals and the predicted values of BMI. And I can line those up against each other. Again, do what kinds of analyses I want with those now that they're saved in the data set. Okay.
So,
Yep.
I have a question.
Yep.
A table. Is that what you're about?
Yeah, this table, yep.
Here, the Stata create automatically the reference category, the first category.
Right.
But what about if I would like to compare all the time with the third category, for example?
Right. So remember from lecture, if you want to change the reference category on the fly, you can use IB and then the number that you want to set as the reference category. So if we want to set 3 as the reference category of Meerkat, I would say IB3.Meerkat instead of just using I.Meerkat. Now, if I fit this model, okay, now look at, I see coefficients for categories 1 and 2 of Meerkat, and they're being compared to category 3. Okay, that makes sense to everybody? So that's the way we can flip the reference categories on the fly. Same model, right? Nothing at all changes about the fit of the model. We're just changing the reference category. That's all. Okay. So now that we have these predicted values and residuals, again, we can do some testing to see if these are, if these assumptions seem justified for this particular model. One additional kind of test that you can do using the test command is to test whether 2 coefficients are equal to each other. Or in other words, if the difference between the 2 coefficients is 0. You can do that by setting those coefficients equal to each other in the test statement. Okay, so are 2 categories equally different from some reference category? We can test that in all hypotheses. So if I run this particular test, which again is setting a different C matrix, now I'm starting to see some evidence that categories 2 and 3 of marital status are in fact different from each other. Again, it's marginal. It's right slightly below the 0.05 level, but there's kind of conflicting evidence on whether or not to keep marital status in the model. Probably, again, especially given the possibility that it might be involved in interactions, I would probably make the decision to keep marital status in light of this evidence. And then once I get around to testing interactions, I can make final decisions about whether it needs to stay in the model. But now that I've flipped the reference category, look what happens to my t-tests. And now it seems like that 2 versus 3 difference might be significant, okay? And that test exactly matches the F test, right? It's a 1 parameter test, so performing that F test is redundant. In this case, I have a test for that 1 parameter by looking at the t-tests. Right? No, this syntax is just testing whether or not they're equal to each other. It's not testing arbitrary values. The only option there is to test whether they're 0, not equal to some fixed value. Yep. Okay. All right. So we can use test statements. We'll keep looking at test statements for different kinds of models. But again, the fact that we can just use tests after fitting a regression model to implement these design adjusted tests of multiple parameters is very, very important. Okay, the fact that Stata makes it that easy to do these tests, fully adjusting for the design features after fitting the model, very important. Okay, let's look then at the assumption of normality in the residuals. So I have this E hat 1 variable saved in the data set. Now I can look at a histogram of E hat 1. I'm going to add a fitted normal density, and then I'm going to add a title to that particular plot. All right. I'm going to go ahead and run this histogram command post estimation using that E hat 1 variable. Okay. It'll take a second for that graph to be plotted and pop up here. But looking at this plot, it definitely seems like I have a skew in the residuals. It definitely seems like they don't fit under that overlaid normal density. Okay. And so I either need to consider a transformation or I need to think about adding some other predictors to this model that might explain some of these extreme values. I only have 4 predictors in the model right now as an initial illustration. So we can kind of take off from here and think, okay, what other predictors do we think might be relevant? Usually, making sure that you have the mean structure of the model well specified comes first before thinking about transformations. Because again, transformations wreck the nice interpretability that you have with these kinds of models. So we usually want to do what we can to make sure the model is correctly specified before jumping to a transformation, okay, just to make sure these assumptions get satisfied. All right, so we have some initial concerns there, but let's look at a QQ plot. So that's the subsequent command here is Q norm. Again, using that E hat1 set of residuals. Okay. Let's see, take a look and see what this looks like. So again, not really good evidence of any kind of assumption of normality being justified for these particular residuals. So we still have some work to do before we were to report any kind of results based on this model. And again, the starting point would probably be to include additional predictors that we think might be relevant, okay, before we think about transformations. All right, so we see that there is evidence of non-normality. So suppose that we couldn't find any other predictors, right? This is the set that we have available. This is the set that we think are relevant. We've tried interactions, none of them are emerging, and we're kind of stuck at this point. And we're stuck with the idea of, okay, maybe we do need to make a transformation to try to achieve normality in those residuals, right? We can generate a new variable called log BMI. And I'm calling that the natural log of the variable BMX BMI. So I'm literally creating this new variable in the data set, which is the log transform version, given that evidence of right skew that we saw in the residuals. So now I have this log BMI variable. And there are some missing values that were generated. For example, people have BMI set to 0 or missing values. And all I'm changing about the regression model now is I'm changing out the dependent variable. Same set of predictors, but I'm changing the dependent variable to be log BMI. So let's take a look at the output that gets generated by doing that. Okay, I still have my 5,230 observations. Okay, so that looks good. But notice now all the coefficients are on a completely different scale, right? Because I took the natural log transformation of the dependent variable. Okay, so I can't talk about now changes in the mean of BMI. Like I can't say that the mean BMI for category 4 of education is about 0.05 lower than the mean BMI for category 1, right? Now we're on the natural log scale. So does anybody remember from lecture what the correct interpretation would be, okay, of these log transform coefficients? How do I interpret these coefficients?
So now we are going to make a transformation for the predictor itself. So
Not the predictor itself. We've just transformed the dependent variable. So if I'm trying to interpret one of these coefficients, let's just take that education category 4. If I was trying to interpret that education category 4, what would my interpretation be? I would say a 1 unit change does what?
Traditionally.
I have to exponentiate it, but a 1 unit change, does it add the exponential?
Doesn't it create don't you start talking about percent changes in the dependent variable? So being HCAT 4 to the default of HCAT 1 is associated with a either negative or 0.04 decrease percent or.
No, see, that's Sarah, that's the mistake we want to avoid.
Okay.
Right, what you just said. So what exponential, but what happens? What am I doing to the dependent variable with that exponentiated value? Am I adding it? I'm multiplying. Remember, that's the key point here. Okay, if I was to exponentiate that coefficient, which I can do in Stata by just saying display exponential of negative 0.047. Okay, I get a number that says 0.954, right? That is what the dependent variable is being multiplied by when I'm in category 4 as opposed to category 1. Or in other words, the mean of the dependent variable is being reduced by 4.6%. Right? If I multiply a number by 0.954, I'm reducing it by 4.6%. Right? So those in education category 4 have a mean that's 4.6% lower than those in education category 1, based on this natural log transformation. So I really have to think carefully about what a transformation does to my interpretation. And the natural log is very often used in these kinds of settings of right skewed continuous variables when fitting linear regression models. Okay. Now, did it help, right? I got to think harder about the interpretation. Did it even help? Okay, let's save predicted values and residuals under new names. Notice I'm not calling them E hat 1 and P hat 1. I'm calling them E hat 2 and P hat 2 so that they're saved in new variables in the data set. And I'm not trying to overwrite those original variables. Okay, now that I have those two variables in the data set, let's look at those same plots again. First of all, the histogram. Okay, where I'm referring to E hat 2, a lot better. Okay, so the natural log transformation seemed to help. Still not perfect, but definitely looking a lot better. Okay, again, we probably would have added other predictors at this point to try to explain more variability. But if we were at the end of that process, we couldn't think of what else to add, and we think that a transformation was warranted, this is looking okay. Let's look at that same Q norm plot, QQ normal plot, normal QQ plot, I should say. A lot better. Okay, so again, the natural log transformation seemed to help with that assumption in this case. And comparing the two models, I'd probably choose to base my interpretations on this natural log transformation. Okay. Now, if I look at the test of marital status, I forget, did we use 2 or, yeah, we used 1 as the reference category. Now, if I look at test 2.meerkat, 3.meerkat, what happens? That assumption about normality completely changed our inference. Okay. Now we have more evidence in favor of keeping marital status in the model, at least the main effect of marital status. Okay. That transformation was crucial in this particular model. Okay. Okay, so diagnostics, very important. And we're just touching the surface with raw residuals and raw predicted values in Stata right now. We're going to dig into this a little bit more within R. Okay, another important plot that you can look at to look at assumptions of constant variance is plotting predicted values against residuals. Okay, again, to see if there's evidence of constant variability in those residuals on the associated with the model that you're fitting. So to do that, I'm going to say graph two-way. Okay, this will create these kind of two-way plots. In this case, we're looking at a scatter plot of predicted values against residuals. Okay, so let's look at this particular, this particular plot. Okay. Okay, so now you see, and you could flip this around if you wanted to. You could have residuals on Y, predicted values on X, really however you want to look at it. The key thing is that you look at it in the first place. That's the key thing. Okay, don't just ignore these diagnostics. Okay, we want to see constant spread in the residuals as a function of those predicted values. And for the most part, we see that here. There are certainly some unusual residuals that we might look into further, and we're going to dig into that again a little bit more within R. But for the most part, we see evidence of constant spread. We see kind of a straight column, if you will, of the spread, the residuals. Okay, if we were looking at it the other way around, we want to see a straight horizontal bar in terms of the spread and the residuals as a function of the predicted values. So this is looking pretty good. We don't see any strong evidence here. We could also plot, using that two-way command, we could plot predicted values or predictor values against the residuals. So look at this as a function of the different categorical predictors if we wanted to. There's a lot we can do as long as those residuals are saved in the data set. Okay, so looking good so far in terms of diagnostics for this model. Remember that you can use the test command for additional tests of multiple parameter hypotheses. So it doesn't have to be for one variable. So I can list an entire block of coefficients. in the test command and get an overall test for that entire block. So if I want to see if both age and education were even relevant for BMI at the same time, I can list all of the coefficients for those two predictors in my test statement, right? And then see, based on this natural log transform model, if there's any evidence that that block matters. Sure, there is. We saw that with education, okay, based on the individual t-test. But the idea here that I'm getting across is that, again, we can use tests for any kinds of multi-parameter hypotheses. It doesn't just have to be one predictor. All right, so clear evidence that adding that block would improve the fit of the model here. So what about an analysis that ignores the weights? Are the weights informative about this particular regression model? This is getting back to that discussion of to weight or not to weight when fitting these models, okay? We've used the weights so far. Are they inflating our variances without producing meaningful changes in the estimates of the actual parameters, right? So just so we have it kind of recent in the output window, I'm going to rerun that weighted log BMI model. Okay, so we have it recent in the output. All right, then notice what I'm doing here in survey set. Okay, I'm clearing out the survey features that resets survey set essentially. Oops. And then in the survey set statement itself, I'm completely ignoring the weights, but I'm still accounting for the cluster sampling and the stratification. Okay, so we're ignoring the weights in the point estimation and the variance estimation for that matter, but we're making sure that the variance estimates still account for cluster sampling and stratification. If you're going to remove the weights, this is the kind of survey set analysis that, or survey set preparation that you want to do. We don't want to remove all the design features entirely. We just want to remove the weights from the point estimation. We still want to make sure that these design features are accounted for in the variance estimation. That's the key point here. Okay? So this is how we would basically turn off the weights in the actual estimation of this model. So I'm going to run these two commands and basically reset my design features. And notice how in the summary here it says sampling weights none. I'm ignoring the weights and fitting this model. Okay. All right. So then same modeling command. All I've done is in all those weighted calculations, I'm just taking out the WIs. Okay, so I'm no longer using weighted least squares. Basically, I'm using a form of ordinary least squares, but I'm still applying linearization to the estimated parameters. Okay, that's the difference. Still using linearization to make sure those other design features are accounted for. Right, so I go ahead and run this model. Now let's kind of just eyeball. Okay, first let's start with gender. On this natural log scale, if I ignore the weights, the estimated coefficient was 0.026 roughly for gender. Looks really important. Okay. If I go back up to the weighted model, oh good Lord. That coefficient is 0. And the p-value is practically 1. Look what is happening between these two models. Okay. If I was to ignore the weights in this kind of analysis, I would reach the conclusion that if you are a female, you have a significantly higher mean BMI. And I'd go write my paper. And I'd say, wow, look at this. When you adjust for marital status, an education category, an age category 3, females have this significantly higher mean on BMI. Okay. If I use the weights, couldn't be farther from the truth. Okay, radically different conclusion. So I'm going to show you how to do this test of whether the weights are informative, but these are the kinds of differences that you can see here. The weights are extremely informative about this particular coefficient, and a failure to use them in this case would be a brutal mistake in this kind of regression model. Okay. So my to weight or not to weight debate in this model, at least as it stands, without any interactions or anything else, there's no debate. Okay. It would flat out be a mistake to ignore the weights here. So if I want to test that formally, okay, remember that approach that I talked about in how we would fit this model to test for the need for weights. I turn the weights off in my survey set. Okay, so like I just did, but I still account for the cluster sampling and the stratification that's available in the data set. Okay, to this model, this is a little wonky in my window here. Let me spread this out. Okay, to my original model with the weights turned off. Okay, I add as a predictor the weight itself. So here's the exam weight. Then I add the two-way interactions of that weight with the predictor variables that I wish to see for which the weights are informative. Okay. If I want to do this test overall, I can add all these two-way interactions. I didn't do that yet. I'm just showing you how to specify one. In this case, for gender, given what we saw in the output here. So to specify that two-way interaction, the continuous variable involved in the interaction starts with C dots. Remember, I don't want to just type that name by itself in the two-way interaction. Otherwise, Stata is going to think it's categorical, and the weight is most certainly not categorical in this model. So I have to use C dot, then hashtag, then the categorical predictor gender with which it's interacting. Okay, so I could rewrite that for like C dot WT MEC 2 year hashtag I dot Meerkat, and then so forth and so on. Okay, we'll come back to that in a second. For now, I'm just looking at this formal test for gender, okay, to see if the weights moderate the slope, the relationship of gender with the outcome. All right. So step one, I add those terms to my unweighted model, including all of my other predictors of interest. Okay, fit this model. I can eyeball the output to see what's going on. The weight variable by itself is significant, and the two-way interaction between the weight and gender strongly significant. Okay, that's telling me that the weight moderates the intercept in the model. As the weight value increases, so does the intercept. Okay, the weight also moderates the relationship of gender with the outcome. Okay. So I can still perform this formal wall test of those additional terms, but just eyeballing the output, I have an answer to my question. The weights are moderating the coefficients of at least the intercept and gender in this case. So to perform that formal wall test, same test command, I just use test with the specific coefficients that I want to test, weight, and then that interaction between weight. But now instead of saying I dot gender, I'm referring to the specific category of gender, 2 dot gender, and the specification of that test command, right? So I test both of those coefficients, and we already know the answer. But this would support the idea that I need to account for the weights when fitting this model. The weights are moderating the values of these coefficients. They are informative about the coefficients in this particular model. In no debate. All right, everybody with me? So this is how you formally test the need for weights. It's never just a vague hand-waving question. We have the tools to test whether weights are important when fitting any kind of regression model. That's what's nice about this general purpose test. We can apply it to a logit model, a Poisson model, a structural equation model. It doesn't matter. Okay? This is a very general purpose test to see whether the weights are informative when fitting a particular regression model. Okay? It's actually attributed to Wayne Fuller. This dates all the way back to a 1984 paper by Wayne Fuller, who said, stop yelling at each other. Here's a way you can test this. 40 years ago. And people still yell at each other. Okay? That's where this test comes from. Okay. Let's see here. That's pretty much what I wanted to illustrate within Stata. And it leaves you kind of wanting because, again, these design adjusted diagnostics are not yet available within Stata. I was really kind of hoping they would be at this point because the literature on how to incorporate design features into regression modeling diagnostics has been around since like the mid 2010s, right? So it's about a decade old at this point, but we still don't have that capability within Stata. So we have to look at these diagnostics with a grain of salt right now because we don't have other diagnostics like DF betas and condition indices and variance inflation factors and all this kind of good stuff, standardized residuals, just not there. Okay, so we're going to look at all that kind of stuff within R when we switch over. Okay, now what I want to do at this point is ask you guys, given what we see in the NHANES data set, how might we improve this model? Okay, the transformation looks pretty good. Okay, but what other predictors could we potentially include that I have not yet included from a theoretical perspective? Right, we're trying to model body mass index, combination of a person's height and weight. Okay, we've included so far gender, marital status, education, and age. What else could we add to this model to see whether or not we can do a better job of explaining variability in a dependent variable? What else could we add? And I'm open to any ideas, just call it out. What do people think?
From the income or.
From what's in the data set, yeah, we have to go with what's available in this list of predictors here that's in the data set.
Yeah, the ratio of income versus.
Income, yep, some measure of socioeconomic status. So in the data set, let's see where that variable is here. INDFMPIR, okay, so I can add that to the model as a predictor. Right, and I'm going to turn my weights back on. I'm going to go back up to my original survey set and turn the weights back on. Clearly, they're important. Okay, what else? What else might be a good predictor? Maybe some interactions.
Maybe some race.
Okay, we don't have race. So let's look at what the race variable is again. It's called RIDREF1. So I'm going to add RIDREF1 to the model. I'm going to space this out a little bit here. Okay, what else?
Blood pressure.
Blood pressure. See if there's an association there. Let's see. What do you think, Ezra? Should it be systolic or diastolic? BP cat. Okay, so you want to use the categorical version. So we'll use BP cat. Do I want to enter it into the model like this?
I found it.
But I'm asking a different question. Is that the syntax I want to use?
Yes.
I dot. Right? Remember, this would just toss that variable into the model like any other continuous predictor. So it's a categorical predictor, so I got to make sure to use I dot, not just BP cat. Okay? Okay, good. So we got a measure of socioeconomic status, we have race, ethnicity, we have a person's blood pressure category. Anything else that might be predicted? Say again. Cholesterol, okay. Are they eating a lot of fatty foods? So that's going to be LBXTC. LBXTC. What considerations do I need for a continuous measure like LBXTC? Age is already in there. What data management do I need to think about when I'm just dumping in a continuous predictor like total cholesterol? Is it possible for a person to have zero cholesterol? Probably not a good idea. Maybe it's possible, but it doesn't really make a lot of sense. So what could we do? What did we talk about? It starts with C. Then center it, right? Make sure that intercept is interpretable. How do I get the weighted mean of cholesterol? SVY what? It's be Friday. You guys are sleepy. SVY what? Do I want just SVY colon mean? Is that going to give me the mean I'm looking for my subpopulation? Subpop. Subpop, age 18P. Okay, then mean of LBXTC. Let's see what that is. All right, so it's 194.4. So I can generate a new variable. I'll call it gen TC cent is equal to LBX TC minus 194.4. That'll give me a centered version of that particular variable. Oops. Wrong button. Okay, so now I have that centered variable in my data set. So I go back to my regression model and I'm using TC cent instead of the original variable. Everybody with me how I did that? So now I have the centered version in my model. Now my intercept's going to make sense. Okay. Now, what else do we need to think about regarding continuous predictors? What am I assuming about the relationship of this predictor with the outcome when I just dump it into a model? What am I assuming?
It's
The
not
relation.
really
Go
variable.
ahead.
And
Go
it's
ahead,
not
Tess.
any of the other variables, and the relationships are linear.
Linear, right. Yep, I'm assuming that I don't have any linearity issues. It's pretty independent of the other variables. I'm assuming that total cholesterol has a linear relationship with the outcome. How can I visualize that assumption? Scatter plot, right? We have the syntax for doing that. Let's just copy that syntax down here. Again, as preparation for fitting this model, and look at a scatter of, let's just look at log BMI on this axis, y-axis, and let's look at TC cent on this axis. Okay. Could look at a weighted scatter plot, but let's just see what this looks like. Okay. Not really strong evidence of any kind of functional form that we can see here. It's pretty cloudy. Looks like a pretty cloudy relationship, not a very well-defined relationship, but I'm not seeing any immediate evidence of any kind of nonlinear relationship. We could look at some simple bivariate analyses, but for now, let's just assume that it's linear, but that's the kind of process you want to go through. We can look at diagnostics too after fitting this model. Okay. All right. So on TC cent, let's toss in one interaction just for the sake of interpretation purposes. Okay, what's a moderating effect that seems like it would make sense from a scientific point of view? Age and gender, right? So the relationship of age with the outcome varies depending on gender. Okay. Let's say we had a hypothesis that gender moderated the relationship of age with BMI. Okay. I can say I want to add to the model I.RIA gender hashtag I.AgeCat3. Okay. So now I'm adding that particular interaction term to the overall model to see if that helps improve the fit. So remember, our starting point for that weighted model in terms of R squared, let's go up here, was about 0.034. Okay, that's where we had with the previous model that we were fitting. Let's see what happens now if I run this entire model all at once. Now I'm up to about 0.087. So I've explained an additional 5% of the variance in that particular dependent variable. Better, not great, better. Also though, look what happened in my subpop number of observations. Adding those predictors introduces the possibility of losing more cases due to missing data. That's in fact what happened here. So I can't really look apples to apples, right? Because I've lost another 1,000 cases due to item missing data on those predictors that we chose. So that's another important consideration here. We're not comparing apples to apples in terms of the overall model being fitted. We also don't see this significance test here because we're running out of degrees of freedom, right? We're adding a bunch of coefficients to this model, and now we're at a point where we can't really get a p-value for that f-test. So that's another drawback given the reduced degrees of freedom associated with the NHANES. All right, so let's see, looks like there's a lot going on, but let's take a second to look at the interaction term. Okay. Remember that when we add that interaction term, try to bring gender back into the picture here. When we add that interaction term, we can no longer refer to these coefficients for the individual predictors like their main effects. We have to get out of that mindset. Okay. As soon as that interaction is in the model, I know that these coefficients represent changes in coefficients, and these coefficients are now conditional coefficients. Okay, so this, remember, we're on the natural log scale, so I'm just going to talk about additive changes in the natural log version of this variable. You can do the multiplication like we talked about. But looking at that coefficient for gender, okay, I would say that among people in the lowest age group, I'm conditioning that coefficient. For people in the lowest age group, females have a mean log transform BMI that's 0.025 higher. I do not say that females have a log transform BMI that's 0.025 higher. I say that young females have a log transform BMI that's 0.025 higher. Everybody see the difference there? As soon as I add that interaction, even if it's not significant, I'm changing what those coefficients mean. They are no longer main effects. Okay? And the same goes for the age effects. Okay? These are not overall relationships of age. Okay? These are relationships of age for males. A reference category of the other variable involved in the interaction. So I would say that among males, conditioning on the other variable being equal to 0, among males, both age categories 2 and 3 have significantly higher means than category 1. That's the relationship among males. This model does not define a main effect of age or gender. It's always conditional. Okay, everybody with me? Okay, so looking at the interaction, because I have to do all that kind of mental gymnastics, do I need this interaction? Okay, this is where the test command becomes incredibly useful. Okay, I want to perform a test of whether this interaction as a whole is adding anything to my model. We could test Aaliyah's hypothesis and say, is there scientific evidence that this interaction matters in predicting BMI? Okay, so my test statement, I'm going to add these two coefficients. Okay, how do I label them? Well, the first one is 2 on gender, so I say 2 RIA gender, and then hashtag 2 on age cat 3. Okay, that's the first coefficient as it's labeled in the output. It's a little bit weird because it's showing the numbers for each of those two variables. I have to start the term, the interaction term itself, with the number dot and then the name of that particular variable. Okay? Then I do the same thing for the second coefficient, 2 dot RIA gender, hashtag 3 dot age cat 3. Okay, that's how I list those two specific coefficients as a part of the test command. Okay, so now I can go ahead and run this because I get those 2 degrees of freedom. Look at the result of that design adjusted F test. What decision do I make about whether it's meaningful to include that interaction in the model? It's yay or nay. It's not adding anything. Okay, I failed to reject that both of those coefficients are equal to 0. So I can simplify my model by taking that interaction out of the model. And that correspondingly simplifies my interpretation of the age and the gender coefficients. I no longer have to condition on the reference categories. Now I can interpret them like their main effects. Okay, everybody with me? This is crucial for making sense of interactions. Okay, so I go back, get rid of that interaction term, refit the model. Now I can look at that gender coefficient as being the overall effect of gender, adjusting for these other covariates. Okay. Okay, what else did we learn? It doesn't look like SES matters, assuming that relationship is linear. It does look like race ethnicity matters. Okay. Compared to category 1, which is Mexican American, categories 3 and category 5 seem to have significantly lower BMI in this particular case. So it definitely seems like there's something going on with race. Blood pressure category certainly seems to matter. So categories 2 and 3 tend to be higher in BMI than categories 1 and 4. Okay. And in terms of total cholesterol, assuming a linear relationship, it doesn't seem like that matters. And we saw that from the big cloud in the scatter plot. It wasn't really a well-defined relationship involving total cholesterol. Okay. So some improvement in the overall R squared, but overall, it seems like race, ethnicity, and blood pressure category are improving things. Let's just look back real quick at the residuals again. I'm going to copy this entire block and call all of these guys 3, right? Based on the most recent model that we fitted here. Okay, so I'm just going to rename the residuals, the predicted values, all to be 3. So that I can rerun this to look at the diagnostics for my most recent model. So I save these in the data set. Let's look at the histogram of the residuals. Still looks pretty good. Okay, a little bit off, maybe some slight deviations. Let's look at the QQ plot. Okay, pretty straight. Not a huge difference. Still a couple potential outliers from any of these predictors. Let's look at the predicted values against the residuals. Okay. Still looks pretty good for the most part, but I think at this point we want to look into a couple outliers that aren't being well explained by this now somewhat large number of predictors that we've added to the model. It still seems like there are some pretty unusual cases on the natural log scale that we want to look at, but we'll revisit those when we get to R and we can actually compute design adjusted versions of standardized residuals to see if they truly are standing out as being unusual. Okay, but overall model looks pretty good, I'd say at this point. We might continue some refinement, but test some additional interactions, but overall it looks pretty good. Okay, so questions about this example, walking through and Stata this kind of process of going back and forth between diagnostics and interpretation, testing the need to use weights when fitting the regression model. Questions about anything that we've discussed in this initial example here? Any questions? Very good. All right, it's about 5 after. Why don't we take a break until about 11:15, and then I will pick back up with the example in R, and we'll show some of those additional capabilities that are available within the Survey Diags package to look at model-based diagnostics. Okay. Okay. Thanks, everybody.
I don't know what happened with today.
No, not all right. Your brain fell down and hurt you and it's the hospital. No, you didn't see it.
Yeah. Let me just let me forward what you said to me first. No time is also send you what I wrote to me. So that you can see yeah. Because I just forwarded it to him. He said, please can you use that bunch?
Well, I don't manage. Yeah, they work with me. You know the concept.
This everywhere. Let me share. Then I will share with you. Don't know what is there.
Oh, you need to.
I'm saying,
You need to take a break.
I would like this to match.
Yes, but just like.
So if we don't use weights, it's the estimation is.
So what I'll do, let me also send you what.
Yes.
For me, I'll just leave that in the page. I will not edit it.
Oh, you can do it.
Yeah, so I'll just.
It's
So if you are, that's fine, just take it.
okay.
And then I'll give you my notes.
Yes.
So we'll just provide.
For the draft of the intro and data and methods, so we'll be using logistic regression, but like we haven't discussed it in class yet, so I don't know the estimation procedure that we will use.
Yeah, that's okay. Just say we plan to use logistic regression, but we haven't reached the topic yet. That's fine.
I just put a placeholder. Thank you. That's fine.
Stress. Yeah, the template that you sent, you sent me email. Because I can't find. I checked yesterday. I thought you should have put this in the template. Yeah. Oh, you sent me the code. Okay. So.
Yes, yes, I will. Also, I have a.
All right, why don't we start back up again here? All right, so now we're shifting gears to R. So again, just kind of the preliminaries if you're working within R. You have to set your working directory to where you've saved all the relevant data. Introduce any libraries that you're going to be using within this particular session. Now, for today's session, we need to add the SBY diags package to the list of packages that we've been working with previously. So notice that my list of libraries in the code for today includes survey diags. So if you haven't already installed that, again, within our studio, you can go to install and then type the name of the package that you want to install, like SVY diags, and then that will install that package and you can then load it as part of your current session. So you have to do that installation first, and I've already done that here. All right, so all in one swoop, gonna load these libraries, set my working directory, read in the data, and then change all the variable names to lowercase. Okay. Okay. Now, we're going to recode age into 3 categories, again, using a form of mutate that we've talked about previously. So I'm going to form that age cat3 variable within the NHANES data frame object. Okay. So let's go ahead and run that mutate function. So now I have age cat3 within the data frame object. And I can look at the distribution of HCAT3, accounting for missing data, specifically for adults, okay, to make sure that that matches with what we saw within Stata, okay? And I see no missing values. All right. So now we have this NHANES data set. I'm going to store all of those categorical predictor variables as factors. So I can use mutate to do that as well, in addition to setting labels for each of the levels of those variables. Okay, so we've seen this syntax before as well, but this is how you can define categorical factors and assign value labels to each of those levels. In addition to doing all of that within the mutate function, I'm creating that natural log transform version of BMI. So you can see how I'm using mutate to do several transformations all at once within the data set. Okay, so handy, definitely a handy function there. So I'm going to run all of this together at once. And now I have that new version of the NHANES data set with those additional variables, so data frame object, I should say. Okay, now I'm going to set my design object like we've done previously and look at a summary of that design object, specifying all of my complex sampling variables. So I'm going to go ahead and run this and make sure nothing looks out of the ordinary with that survey design object using linearization for variance estimation. I'm going to create my unconditional subpopulation design object using that subset function applied to the original design object for that condition that age 18P is equal to 1, and then summarize that, make sure everything looks okay. All right. Now, I've done the preparation needed to fit that initial model using the SVY GLM function within survey. Okay, so this is the big difference here, is that we're now using SVY GLM, which again can fit a variety of linear regression models. The default linear regression model that the default model that SVY GLM fits is linear regression, assuming a normally distributed dependent variable. The way that the syntax works with an SVY GLM, the first argument to that function is the model formula. All right, so in that model formula, we have the dependent variable on the left-hand side of a tilde. And then on the right-hand side of the tilde, we have the different predictors separated by plus signs. And I'm not specifying all these variables as factors because I already did that in the data frame object. So I don't have to do that again. It's redundant in this case. All right, so I'm just listing the predictors as they are: gender, marital status, education, and age cat 3. Again, matching the model that we were fitting within Stata. All right, second argument is the subpopulation survey design object that we created using subset. So the second argument that I'm providing is sub NHANES SVY, being explicit about the fact that I want to focus on the adult subpopulation unconditionally. All right. And then finally, I'm saving the results of this linear regression analysis in a new variable or a new object called BMI SVY. All right, that way I can refer to that new object for testing of coefficients, for summarizing results, things of that sort if I want to. Okay, so let me run this one line here. Okay. In R, no news is good news. So it says it was able to successfully fit that model and create that new object called BMI SVY. Now, if I want to look at this, the typical regression output that we look for, like estimated coefficients, standard errors, p-values, etc., I can use the summary function and apply the summary function to that new object that I created using SVY GLM. Okay, that's where I'm going to see all that output like we saw in Stata. So I'm going to say summary, BMI SVY. Now in your R console, you're going to see the call of that function, the survey design object based on the subpopulation, and then the weighted point estimates of each of those different coefficients. And you can see where it's useful to have those labels from the mutate command, because now I can see gender F, previously married, never married, etc. If I had just left those as numbers, all we would see in this output is numbers like we saw in Stata. Okay, so having those labels is helpful, and that will help us make sense of these different coefficients, but you see the same output that we saw within Stata. Okay, all right. Now we have that object saved So now we can leverage that object to look at our diagnostics, okay, after we've created that object from fitting the model. So in the very simplest sense, if I just say plot and then type the name of that object containing the results of my regression, let's see what happens. Okay. Now, it's interesting the way survey operates. When you apply that plot function to a model object, you see a sequence of residual plots when using the plot function. So you can see in the console, it's waiting for me to hit return to see the next plot in a series of diagnostic plots. So if I hit return, there's my first plot. Okay, and again, I like what R is doing better than what Stata does in terms of residual diagnostics. Okay, so here's the default. You see these residuals against the predicted values as the first plot, okay, with unusual cases labeled in the output. So it's telling you what row IDs are associated with these highly unusual residual values in case you want to go into those rows and see if something's unusual about that particular case. Okay, so that's helpful just for trying to find who's outliers and what's going on there. Let's take a look at the next plot by hitting enter. Okay, now without having to type anything, I get that QQ plot, which again was showing this big deviation from what would be expected if the residuals were following a normal distribution. Again, with the row IDs of these highly unusual residuals that we might want to look into, okay, to see what might be going on with those particular cases, right? So some concerns about normality here and some potential outliers. Next plot, okay, just another form of square roots of the Pearson residuals standardized against predicted values, again, to try to identify unusual values. There's also a fitted regression line to that plot. And if we see no evidence of a pattern in the residuals, that fitted line should just be a straight horizontal line. For the most part, we see that. There's a slight positive trend, but for the most part, that looks okay. Okay, we do want to investigate those potential outliers though. Okay, here's the next plot, residuals against the leverage of these individual cases. Okay, so cases with extremely high leverage, those are cases where they're having a big impact on the estimates of those regression coefficients. And we're going to look at that with the SPY diags plots in a little bit more detail. But still, we see some cases that are considered highly unusual residuals. Interestingly enough, though, they're kind of in the middle of the pack in terms of the leverage that they're having on the estimates of those coefficients, right? So they're not having a huge impact from a leverage perspective, but there is this one pretty unusual case out there in terms of leverage. We're going to see if that pops up by looking at these Cook statistics as well in survey diags. But I really like this because it's a very cool feature where you don't have to run a lot of syntax. All you have to do is use this plot wrapper function for the object created by fitting that model, and you see all these standard diagnostic plots. So it's almost impossible to avoid them. Okay, all you have to do is run one simple function. All right, so that's pretty cool. Based on that model object, we can also create predicted values. So here, I'm creating a new object called BMI pred, which contains the predicted values based on the regression model fit in BMI SVY. I'm not saving the standard errors right now of those predicted values. So that's just an object. But then I can plot the actual values in the survey design object, the actual values in the data, against the predicted values that I just saved. See if there's evidence of a correlation there. Okay, see how closely those predicted values are lining up with the actual values in the data set. So that's another kind of simple plot, just kind of gives you a sense of fit. And as you can see, this initial model that was only explaining about 2% of the variance in the dependent variable, you know, ideal fitting model to see close to a straight line, this is still a cloud. Okay, so there's still a lot of unexplained variability in the predicted values, at least based on this initial model. Okay, so diagnostics, again, like we saw in this data application, not great on the surface, and we want to think about other possible approaches and next steps with this particular model. If we want to test individual terms like we were using with the test command within Stata, after fitting that model and saving the model object, we can apply the reg term test function within survey to a particular term from that model object, okay? So the way that reg term test is working, and note the capital T's in this function, because R is case sensitive about these different functions. First, we have the object contain the results of the model fit. Then we have, after a tilde, the term or terms that you wish to test simultaneously against being equal to 0. So unlike in Stata, where we had to list each individual coefficient in the test statement, in R, we just have to list the term. And that will bring along all of the coefficients that were estimated for that particular term. Okay, so we don't have to do quite as much the amount of typing as we did in Stata. Okay, and you can use a couple different ways to do this. Walled, which is the default, is doing what we talked about in lecture. Okay, where we're computing that walled F statistic and testing the null hypothesis that all those coefficients are 0. Lonely combined with Alistair Scott of Rouse-Scott fame to work on a design adjusted likelihood ratio test. Okay, so that's another capability within R, and this will become more relevant when we talk about generalized linear models like logistic regression, Poisson regression, etc. But you can also use a design adjusted likelihood ratio version of this test using that LRT method. Okay, as we'll see, either way gives you very similar results. All right, so I'm going to run both of these at the same time. Okay, so looking at that walled test for Meerkat, here we see again marginal evidence, Meerkat being important. Okay, probably may or may not decide to include it. And then the design adjusted likelihood ratio test, which uses the Rouse-Scott methodology. We'll talk more about that next week. Really arriving at a similar conclusion, right? The p-values, one p-value is like 0.1, the other p-value is about 0.13. There's some arguments for the walled test being better for small samples, like likelihood ratio test, you tend to want larger samples, but they're both giving us the same general conclusion. There's very weak evidence, if any, in the context of this model to keep Merrill status there. Okay, so we have all those different design adjusted forms of the testing that we can do for terms in that model. So again, until we start testing interactions, probably keep marital status in there to begin with, but this gives you like the analog of how to run that kind of test, similar to what we were doing with Stata. Okay, so given what we've seen in those initial diagnostics, now we might work with the log transformation of BMI as a dependent variable. Again, if we've exhausted all the other alternatives in terms of potential predictors that we could add. So in that SVY GLM function, all I did here was change the dependent variable to be log BMI. Everything else about the function stays the same. Okay, like we did within Stata, I'm just changing the dependent variable, and I'm using the one that we created earlier in the mutate function, okay, to get that natural log transformed BMI here. So I'm actually going to run that model and the summary of its object simultaneously here, so we can take a look at it. And here again, you see all of those estimated coefficients now on that log transform scale. Now let's look at those that same sequence of plots. Again, just running the plot function on that new model object containing the log transform results. Okay, here's residuals versus fitted. Again, we still see these outliers as popping up even on the natural log scale. Okay, so it's definitely worth looking into seeing what's going on there in terms of those particular cases. Why do we see, and even more clearly in this plot, a bunch of straight lines for the predicted values? Okay, why do we see this unusual plot where it's not just a cloud of values for predicted values, but we see a series of straight lines in this residual fitted plot? Like, what about the model is causing that? Why would we just see a bunch of discrete values for those predicted values? Curio?
Perhaps maybe some of our predicted variables are categorical.
Well, in this case, they're all categorical. Remember? Every single variable is categorical. So there's only so many combinations of values on these variables that can be used to produce predictions, right? So if we had one 2-category predictor and a second 2-category predictor, we're just going to have 4 lines in this plot because there's just going to be 4 predictions. That's what we're seeing here. So that the fact that every predictor is categorical is what gives these plots this kind of unusual appearance where we're not seeing like a smooth distribution of those predicted values. It's just because everything's categorical. Okay, so that's looking okay. QQ plot's still not great. Okay, there's still some deviations in terms of these residuals. So again, we haven't tried other predictors at this point, but there's still some deviations here. We do want to take a look at those outliers. Okay. Same idea here with that scale location plot, seeing if there's a relationship between the residuals and the fitted values. Doesn't appear to be a strong one, but we still see evidence of the outliers. And then again, looking at the leverages now on the log transform scale, those cases that are being identified as being unusual, they're still kind of middle of the pack. There's still one case that seems to be having unusual leverage on the fit of the model, so we might try to identify that case as well. And we're going to revisit this with SVY diex. Yep. Kira, did you have a follow-up or?
Just a follow-up on the vertical line. So
Yeah.
like the vertical lines are okay, as long as we have that horizontal.
Sorry, I'm just going backwards here. Yeah. Yeah, no, this is fine. Again, what we want to look for is even if we have, 20 or whatever it is, possible predicted values, we want to make sure that there's not any particular group where the residual variance is much lower than in the other groups, because we're assuming that residual variance is constant, no matter the predicted value. So in some sense, this kind of applies actually a little bit easier to read for testing that assumption of constant error variance, because you're only looking at these lines rather than a big cloud. Okay, but that still the same idea. It's okay if the plot takes that appearance. We just want to make sure that residual variance is constant. If it's not, then we might have to think about alternative approaches to fitting the model. But this looks okay for now. Yep. Newman?
So in a body test and equilibration test, compare it with the arbitrary value 0.1. So
I'm sorry. What do you mean by arbitrary value of 0.1? I'm still not following you. What do you mean by arbitrary?
we have two p values. One
Yep.
for body test is
Yep.
0.09.
Yep.
Second is 0.12.
Yep.
So if we have a alpha is 0.1.
Oh, you're fixing alpha to 0.1. Yeah. Again, using the magical idea of kind of Fisherian hypothesis testing. Sure. You keep Mercat based on the wall test, but you wouldn't based on the likelihood ratio test. I look at that and I say it's weak evidence no matter what, right? I don't know. It's, different statisticians operate differently, but I'm not one who's prone to fix alpha values and say it's a magic number. I just want to see strength of evidence, and I'm not seeing strength of evidence here. Okay? So you could report both and say, either way we look at this, again, we might have evidence in one case, not in the other. I'd probably still keep marital status in there when testing for interactions, either way. But yes, if you're going to enforce a strict alpha level of 0.1, you can report the wall test and say, sure, I have evidence there. It's just not strong evidence at all. Okay. I don't like treating p-values like magic numbers. I'm more the Bayesian side of me, but yeah, I don't really look at that and I say, wow, different conclusions. I don't see them. Okay. All right, let's go back to the code. Saving predicted values on log transform BMI and then plotting them against the actual log transform BMI. This plot, again, not great. There's still a lot of unexplained variability in the actual BMI values based on these predictors. And if you want to apply reg term tests to multiple predictor terms, not just one, you have to separate the terms by a plus sign within reg term tests, like you would in a model specification. Okay, so this will give us that test we were looking at in Stata, where we were looking at all the coefficients for age cat and all the coefficients for education cat. Okay, so if I run this particular test, again, we see the same result where clearly these variables are important, but that shows you how you can list multiple terms in the way that R is doing this to get tests for multiple predictors at the same time. All right, so that's giving you that design adjusted wall test of multiple predictors. So this is again, just to reiterate, this is the design adjusted version of like hierarchical regression or testing for change in R squared. You're looking at blocks of predictors. This is how you would carry that out. Okay. Now, what I want to look at in more detail is again, these additional design adjusted model diagnostics that are made possible by the survey diex package. Remember, we loaded that package separately outside of survey. It does work together with survey, but it's still a separate package altogether that you have to load within ARM. So in that particular survey diags package, there's all these SVY something functions. So you can see in the syntax here, there's like SVY cooks D, there's SVY DF betas, there's SVY standardized residuals, there's also SVY collinearity diagnostics, there's SVY VIF. I haven't gone through every possible function in this particular syntax, but basically this package is implementing all the design adjusted diagnostics that are available in the literature to date. Like I said, they just released a new version of this package in May that reflected all the more recent updates. Okay, so all of these different functions are available in that package. And the basic way that most of these functions work, you provide as input a model object. That's this mobj function. So that's the first argument to each of these functions, is the object that contains the results of your fitted linear regression model. And then you also have to specify the stratum and cluster variables again. Okay, it's a little bit redundant, but that's the way that these functions are working. They're forcing you to specify what these variables are containing these design features. And then for some of the functions that automatically create plots, you can add this argument that says do plot equals true. And that means it'll automatically generate that diagnostic plot as a part of running that function. All right. So the first function that we're going to look at is for SVY cooks D. So cooks D statistic is a diagnostic quantity that kind of simultaneously incorporates residual and leverage. Okay, so it's kind of like in together. Are there cases that are both outliers and having high leverage on the fit of your model? So it's kind of a useful simultaneous assessment of the overall importance of a given point in the fit of the model. So not only am I saving that in a new object where I get those Cook statistics for all my cases, I'm adding a plot that makes sure it plots those Cook's values to see if any are unusual. So when I run that particular function, okay, what you're going to get is this plot for each of the sample elements in the overall data set. Okay, we see the value of that Cook statistic. Okay. And for these different sample elements, you can see, again, this is like that, I think it was 4,500 or whatever that case may be. You're looking for those cases that have an extreme amount of influence at the top of this kind of plot. The nice thing about this is that the calculation of the Cook statistic in this case, again, incorporates all these design features and the uncertainty associated with each of the predicted values for these different cases. So this is a handy feature, and you can go through and try to identify, okay, which of the elements in this particular data set has an extremely unusual value. That information is saved within this mcook object. So like if I just look at the first 10 cases, oops, sorry. I'll just list the values here for mcook. You see for each of the rows that were fitted in that data set, you see the value of their Cook statistic. So you can go through and find, for example, the maximum value of this vector. You can look at what case is associated with that maximum value, but all of these can be saved to see which of these cases have an extremely influential effect on the fit of the model. Okay. Okay, so that gives you the plot automatically, and you're looking for the most extreme cases, trying to identify those in this particular case.
So the SVY XD,
yeah,
it's within the SVY diags.
Diags, yeah. It's not in survey, it's in SVY diags. Right. Yeah.
It's not.
Is it, make sure you're using the capitals. So it's SVY capital C.
You didn't change your code.
Yeah, no, it should be there. Did you load the survey diags package? Should be there, so I'm not sure why that's happening. Yeah, you did run the library line? You did, because you have to install and load. Yeah, okay. Yeah, it should be there. So I can maybe take a look after. All right, so another one is DF betas. So DF betas will tell you for a given case, if you leave that case out of the regression model fit, how much are each of the coefficients going to change in magnitude when you leave that case out? Okay? So if you identify a case, for example, with a large Cook statistic, you leave that case out of the fit, how much are each of the estimated coefficients going to change in quantity? Okay, so I'll go ahead and run this line, and we'll take a look at what DF betas looks like here. Okay. Now, notice, maybe I printed too much. Sorry, I printed too much here. Let me see, what's the best way to do this? Trying to just show you like the basic structure of this. What you're basically going to get is a matrix of, for each of the cases, the actual values of the coefficient change for those particular cases. So you can use that information again to see which of these different coefficients are changing significantly if I were to drop out that particular case. Trying to figure out though the best way to summarize the values here. Because it's in, I think it's in a list form actually. I have another example that I've worked on for this, so I'll post an example of accessing the DF betas information here after the class is over. So I'll post an announcement about that, just how to get at those. Okay, but again, you can just trust me for now that that's going to give you these design adjusted versions of the DF betas that come with this. Okay. Standardized and studentized residuals. That's what SVY STD res is for. So not looking at the raw residuals, but dividing by the standard errors of these estimated residuals in looking at diagnostics that account for the fact that some predictions come with more uncertainty than others, but where those standard errors, again, reflect the different design features. So this particular plot, and I'm saving these residuals again in a new object, this particular plot will show me, once I take into account the corrected standard errors of each of these residuals, are there cases that fall outside of these kinds of limits of plus or minus 3 standard deviations, if you will, the way that these residuals are being computed. So that's what the red lines represent in this particular plot, is basically the standard deviations of these residuals, or the residuals on this standard deviation scale. Okay, so you're scaling each of the estimated residuals by their estimated standard deviations. And this is where you can identify any cases that have a residual outside of those limits of 3 and -3 on this standardized distribution would be worth looking at further to see if they're having a big impact on the overall fit of the model. Okay, and then given that standardized residuals object, you can look through the individual cases and see what their standardized residuals were, okay, to try to make a decision about what cases you might drop and what cases you might work with further. Okay, so that's a handy way to get not the raw residuals, but the standardized residuals to look at to see if there's evidence of, again, additional extreme outliers. Okay, so there's a handful of cases that we might work with, and you can go back to what the plot function was telling you within the survey package to see what the IDs of those particular cases might be. But you have the standardized residual values within this object, and you can take a look at what those values are for individual cases if you need to. Okay. Now, I haven't gone through examples of SVY collinear and SVY VIF, but this is where you will get collinearity diagnostics, including condition indices, to see if predictors are highly correlated with each other, in addition to variance inflation factors for each of the different predictor variables that you might include in a model. So those functions are there available as well. And they can tell you how big of a deal collinearity is. Like if you're having particular predictor variables included in a model that are so correlated with each other that their estimated standard errors might be inflated or their signs might be switched with each other. Okay? There's just multiple steps to getting these diagnostics. And I think what I'm actually going to do, we've been walking through another study that works with these. As an additional document in the readings, I'm going to post a draft of that document that kind of walks through the use of all these latest functions. There's additional examples in the book, but we've looked at a document posting additional examples of these, so I'll post that up on Canvas and everybody can take a look at it and see more detail about the use of these different functions. But the online documentation kind of walks through these as well in this particular case. But the message here is that there's nothing like these collinearity diagnostics within Stata. Okay, this is only going to be available in R. So all this stuff like DF betas, Cook's D, the standardized residuals, we're only going to see this within R at this point. You're not going to see it within SAS or SPSS. It's only really been programmed in R. So if you really want to do this kind of thorough diagnostic analysis, it's important to work with the information in R to extract this stuff. So, okay. So I'll post that after the class when I get back. And then this additional code is just showing you what happens when we ignore the weights and how you might go about performing that particular test of the need for using weights in estimation. So notice in this design object, I'm ignoring the weight argument. So if you ignore the weight argument, that just sets everybody's weight to be equal to 1 in the data set. So this creates a new design object called NHANES SBY no weight. And this is what you might use for doing that test of the need to use weights. And notice that when you do this, you get a warning message in the output saying that you're assuming an equal probability sample. You haven't specified any weights or anything like that. So it's kind of a warning message to you saying, are you sure you want to do this? Like ignoring the weights entirely. Okay? Then you can summarize that object where we're still accounting for the cluster sampling and the stratification. Excuse me. And notice that the probabilities are all 1. Okay, so by ignoring the weights, you're assuming everybody has the same probability being selected, but you're still accounting for the stratification, the cluster sampling in the design. And that's what's important here. All right. Create the subset of that object to work with the subpopulation. And then you can refit the model using those or without the weights being accounted for just to see the impact of the weights on estimation. Look at the summary of that model. Okay. And line these up like we did within Stata. But again, to formally test the need for weights in R, you'd have to take that model, okay, and add to it, like suppose again we want to test gender, add to it the final weight within the design object, and then this interaction between the final weight and gender, for example. And I can use an asterisk to include these terms in the overall interaction. So this would say add to that unweighted model the final weight variable itself, and then the interaction between gender and that final weight variable. And that's George. Yes.
So that's very to denote the interaction.
The two-way interaction involving all possible dummies of the categorical variable. The colon that you use within our notation is referring to the individual indicator variables that might interact with other variables. The asterisk is capturing everything. So I'm using that as the general notation here. Yep. All right, so I'm going to fit this model, again, without the weights turned on. Okay, I can look at the summary. Oops. Right. And again, like we saw within Stata, it looks like the weight is moderating the intercept, and then the weight is moderating the coefficient for gender. Okay, so same kind of conclusion we saw within Stata. And then if I wanted to do that formal test, I would say reg term test, name of that design object, which is LG, BMI, SBY, and W, and then the terms, which after a tilde are going to be weight, mech, 2-year, plus weight, mech, 2-year, asterisk, RIA, gender. The default method will be the wall test. Okay. All right. So then I get my formal test of whether adding those two terms made a significant change in the fit of the model, or in other words, that the weight variables are moderating the relationships of the other coefficients with the outcome. And based on that conclusion, I would certainly see evidence of that. If this test was not significant, that tells me that I can probably get by with the unweighted model without any kind of significant changes, right? Because it's testing whether all those weight terms have a coefficient of 0 in the context of that model. Okay. Everybody with me with how that test is carried out within R? Same thing we did within Stata? Any questions about this process? Okay, good. So that's what I wanted to illustrate within R as well, just about, again, fitting these linear regression models. One thing I do want to mention is that SVY diags, all of these functions here, only relevant for linear regression. Okay? Everything in SVY diags, all the theory that's been developed for these design-adjusted diagnostics, only relevant for linear regression. Okay? These ideas haven't been extended to other kinds of residuals and so forth that we deal with in logistic regression, survival analysis, things like that. SVY diags, all that theory only applies to linear regression. So next week, when we talk about logistic regression and we get into other kinds of generalized linear models, we're going to talk about what other techniques and tests have been adapted for diagnostics in that context. Everything here is just for linear regression. Okay, so important to keep that in mind with SVY diags. And like I said, I'll post a more worked out example of that a little bit later. Okay, so questions, comments, thoughts about the R illustration? Any questions or comments about R? Yep.
You want to see? I think I try with head DF betas and.
Yeah, like if we look at names, it's escaping me off the top of my head right now, like what we can look at within DF betas. Yeah, it's not even showing names. So I have some.
I tried head parentheses.
Yeah.
Now head HEAD, sorry.
Oh, head. I see.
Head, I don't know how to say. No, only DF because your object is DF dollar. I put dollar and the name of the.
We call it like up here, so.
Dollar. And now you can see the parts. It's better to see.
Okay, yeah, like I said, I've worked this out, so I'm forgetting off.
In my case, I can see everything.
Okay, yeah. I'll show you the document, but in this example we've talked about, I picked out cases and showed their DF beta, so I'll post that. Okay, other questions about the R syntax? Any other questions? Yep. Can you speak up a little bit? You said Stata?
Yeah, Stata.
Okay.
On the right hand side of those variables, you're going to do the diagnosis variable expression.
Right.
The other variables.
No, yeah, the predictors are not touched. No. Yeah, we're no, yeah, we're in the example that I looked at here, I'm only log transforming the dependent variable. I didn't log transform any of the predictors, right? Because in this case, all of our predictors are 1, 0 variables. So it would make sense to log transform them. Yeah, we're only log transforming the dependent variable.
Yeah. To transform the dependent variable, it's not automatic.
Right. We did, yes. Remember that was the two-way plot that we looked at of residuals against predicted values. That was the plot we were using to check that assumption. We did look at that, yeah.
Professor,
Yep.
I have a question instead. Because here advised me to make a model using independent variable as a residual.
Right. So to see if there's any relationship between the residual and a given predictor.
Yes, I did that for our data.
Yeah.
But the results is just some weird results, for example, because p value all the time is 1.
Yeah, I'd have to look and see what you did. Like, so like what I was getting at is you could, for example, well, I was trying to think, what was the model we were using? So if I looked at, for example, a regression of, we had TC cent. So like if I was to regress E hat 3 on TC cent like this, to see if there's a relationship of the residuals with TC cent, like that would tell me that it seems like there's not a consistent relationship between TC cent and residuals. That's what I was hinting at, but you can look at that to get a sense of, based on individual scatter plots, does it seem like there's any kind of relationship? And of course, in these, we want to allow for nonlinear relationships to see if we're missing that. But yeah, if you send me your output, I can take a look at what you did. So, yeah. Okay, other questions on these examples today? Okay, if not, I think we're all set then. So again, I'll look for the introductions and data and methods by 5 o'clock today. Try to get you feedback over the weekend, next week, and leading into next week, just making sure that everybody's on the right track. And then Monday, again, Young Chow is going to be giving a guest lecture on logistic regression. And then Wednesday will be our lab, and Friday, again, there's no class, okay, for the 4th of July holiday, okay? Okay, I think we're all set then. So everybody have a good weekend, and I will talk to you next week.
Thank you.
So, okay.
Yeah. So the category, you can apply the transformation category.
Well, wait, your dependent variable is not categorical. So it has, we're treating it like it's continuous, but that's why you see like, again, the straight line value. But yeah, I mean, again, like with a transformation, like you want to have exhausted all of the predictors, right? So in the homework, you're considering 3 predictors. You can try a transformation, but it may not work in all these cases, especially since this is a discrete variable. It only has 11 possible values. So you can try it, but your residual plots are always going to look a little different just because it's discrete.
Today's class, this one. So here we have some trend, like it's not a constant. That's why we use the log transformation.
Log transformation was again normality. We were doing that in response to normality, lack of normality. It might help with non-constant variance, but there are certain variance stabilizing transformations that are better for non-constant variance, such as the square root. So if you think that this reflects non-constant variance, I don't see a big problem with it. But if you're worried about it, you might also try a square root transformation. That's another example of a transformation that has a property of stabilizing there. So that's one you could consider. But yeah, we were primarily using the natural log transformation in response to the plot showing lack of normality, not in response to this.
So, but in my opinion, like it shows that these are not known constant, because if you see the scale that -20 to 40, and after the log transformation, just now just the scale.
That's fine. So again, this is very subjective in looking at these informally. So when possible, we want to try to look at formal methods. But yeah, based on these informal plots, it seems like it helped. But it was that the original intention was to address the lack of normality. So it helped in this case. It is on campus. Yeah, it's already, it's in the lab.
Some changes of the.
Oh, no, that kind of stuff on the fly, I don't usually keep, so, but no, yeah, it's just the raw code is up there.
Okay, we need to also, I'm just trying to get all this code, but need to check the videos and as well.
I mean, I can email it to you if you want, but I had never intended to kind of share the stuff that I'm doing. on
Yeah, the last
fly,
one.
So,
So here, yes, in this is the last one. Actually, here, Professor, I think these variables 1, 2, 3,
Right.
4 to just make more efficient. So like again, we are having the transform dependent variable. Even we are adding more variables. So by adding more variables, at the same time, we are having the log transformation for the dependent variable.
yeah, we're keeping that log because we made it, it's kind of backwards in this case because we looked at that log transformation first. Ideally, I'd want to put everything back on the original scale, add predictors, then decide whether to transform. But in this case, we just stuck with that because it seemed like it made a noticeable difference in terms of that residual distribution.
So if we just add these variables and take BMA as a simple dependent variable without the log transformation, so will it have impact on the?
We don't know.
models?
Yeah, you can look, but yeah, I usually reserve transformation as being like a last resort. So I was just illustrating it here to show how you would use it, but I do whatever I can to add the right predictors to the mean structure. And only then would I consider transformation kind of as a last step. If I'm still seeing that the assumptions are being violated.
So this is the more prudent approach to get the log transformation and adding the more variables.
No, that's not what I said. So sorry, I was just illustrating how to use the log transformation, that's all.
Okay, otherwise.
Better in practice, because again, it makes my interpretation more difficult. So better in practice, keep the original dependent variable, make sure you get the model well specified, and only then transform. I was just illustrating.
Okay, just for the understanding. Yeah, thank you.
Yep.
I think your problem is setting weights. Because in the beginning, you have to set. As I